Let's talk about rings. So the first question I have is why? Why would we need to talk about rings? And the answer to that is because five and six membered rings in particular are very common in nature. So it's a very common ring size for the compounds found in nature. So let's look at some examples. So one category could be something that we call natural products. So a natural product is a compound that's produced either as part of its main metabolism or as a byproduct of a metabolic pathway that's produced by something in nature, like a plant or a sponge or an algae, things of this type. So for example, we have things like limonene. That's the major component of orange oil. Then there's carvone, which is found in both spearmint and caraway oils. And then a couple of compounds that for some people are essential to life, nicotine and caffeine. Nicotine is an example of something called an alkaloid. So an alkaloid is a naturally occurring compound that contains nitrogen. So it's a natural product with nitrogen in it. And then caffeine you could also think of as being an alkaloid for the same reason. Biomolecules. So these are molecules that exist in our bodies and are part of our metabolism and functioning. So for example, this first one is an example of what we would call a sugar. So this is a sugar. That's sort of a common term for it. A more technical term is carbohydrate. So notice that the way this is drawn, we have these three bonds that I just highlighted are bold, they're coming out toward you. This particular molecule is drawn in a format that we're not going to be using in organic chemistry, but you'll see if you take biochem. And this is what's referred to as a Haworth projection. So sugars, or carbohydrates, are characterized by the fact that they contain carbon, hydrogen, and oxygen, and they have lots of OH groups associated with them. This one is a form of D-glucose, is the name of the molecule. So this is alpha-D-glucopyranose. Some other biomolecules. Here's ribose, that's a part of the RNA structure. And then on the far right, thymine, which is a part of DNA. And then finally at the bottom, we have two examples of human sex hormones. So these are two of them, testosterone on the left and estradiol on the right. So what we can see in their structures of these two hormones, is that they have a very similar structural motif. So they have these three six-membered rings arranged in a particular way, and then appended onto the end of that pattern is a five-membered ring. So what I've highlighted in each of these molecules is this piece right here, which is the backbone of all steroids. So this is the steroid skeleton. Okay, let's get into the conformational analysis of cycloalkanes. So here's a bunch of rings. Now, the rings get divided into these categories. For example, 3 and 4 membered rings are classified as what we call small rings. 5, 6, and 7 membered rings are called common rings. And then there's a little notation down below. Medium rings are 8 to 12 carbons, large rings 12 or more. Okay, so we don't really need to worry too much about all those terms. We're going to be focusing on the first 4. So 3-membered rings through 6-membered rings. So let's get into it. So first of all, ring strain. What is ring strain? Well, that's just a catch-all term for all the sources of strain that exist within a ring. Now, to remind you what we talked about in the first video in this set, strain, or strain energy, is the difference between an experimental heat of combustion and a calculated one. So I gave you that definition, but we didn't do much with it except to calculate total strain energies for different conformations. But let's see how this idea would come into play. We can do this more easily with the rings than we could with the acyclic molecules. So let's just look at this table of data. Now, all of these numbers, by the way, that I'm giving you, for example, the value of the Ghost-butane interaction, that's 0.8 kilocalories per mole. Hydrogen-hydrogen eclipse, that's 1 kilocalorie per mole. You don't have to memorize any of these numbers. You just have to know how to use them. And the reason for this is because depending on the table that you look in, there's going to be some slight variation in these numbers, but they're all going to track with the relative same magnitudes. Okay, so for example, you might look up a Ghost-butane interaction and find instead of 0.8 kilocalories per mole, that someone is reporting it as 0.7 something or 0.9 kilocalories per mole. So there's a little bit of variation, but the main thing is to understand how to work with the numbers. Okay, so let's look at this set of data. This is heat of combustion data for some of these smaller size rings. And so let's look at what's going on here. So we're going to focus on cyclopropane. Okay, so cyclopropane, you take some cyclopropane, you put it into a bomb calorimeter, you measure some out, you know exactly how many moles you have, you ignite your sample, it combusts within the calorimeter, you measure the temperature change, you calculate the heat of combustion. So when you take cyclopropane and combust it, its heat of combustion is 500 kilocalories per mole. That's the amount of energy that's released. Okay, so remember, combustion is exothermic. So all of these numbers refer to the amount of energy released in each of these processes. Okay, so the next thing you do is you head on over to the computer and you do a calculation. So this is going to be your computer modeling. And so what you tell the computer to do is to come up with a heat of combustion for cyclopropane based on the assumption that it's strain-free. And you're going to use this number here, or this approach, to do this. 156 kilocalories per mole is the energy of a strain-free CH2 group. Which you might remember from our very first packet is called a methylene group. So each one of those, each CH2 group, assuming that it's not involved in any kind of strain interactions with any other part of the molecule, the energy is 156 kilocalories per mole. The N just refers to how many CH2 groups you have in the molecule. So for cyclopropane, we have CH2, CH2, and CH2. So we have 3 of them. So it would be 3 times 156, which is 468 kilocalories per mole. You subtract that number from the experimental value of the heat of combustion, and you come up with the strain energy of cyclopropane, which is 32 kilocalories per mole. Okay, let's look at this a different way. So same information, just presented a little bit differently. Whether we're combusting actual real cyclopropane in a bomb calorimeter, or whether we're theoretically combusting cyclopropane by using a computer program, the reaction is the same. And so if we look at the diagram down below, here's the balanced equation for the combustion of cyclopropane. So remember that combustion is burning something to completion in the presence of oxygen. So 2 cyclopropanes plus 9 oxygens, when combusted, yields 6 CO2s and 6 waters. So it doesn't matter whether it's real or imaginary cyclopropane, it's governed by the same equation. So that's one thing. So let's say that the energy of those products, the carbon dioxide and the water, is this line here. What we know from the calculations above is that when you experimentally combust cyclopropane, it releases 500 kilocalories per mole of energy. So let's say that that value is up here. Here's the actual cyclopropane. And here's the amount of energy it releases. And so because it's an exothermic reaction, the products are lower in energy than the reactants. So the cyclopropane is going to be higher on the energy diagram. Our imaginary or theoretical strain-free version of cyclopropane is over here. So this is a theoretical. And when it combusts, 468 kilocalories per mole of energy are released. So the theoretical version is lower in energy than the actual version. The difference between the two, which is right here, is the strain energy. Let's take a look up at the chart up above at some of these strain energies. So from cyclopropane to cyclobutane, you go from 32 to 26. Okay, and as we'll see, cyclobutane has inherent to its structure an ability to relieve some of the strain that cyclopropane can't, and we'll see why in a few minutes. When you go from a 4-membered ring to a 5-membered ring, notice that there's a big drop in the strain energy. Okay, so we go down to 7. So right here, there's a big drop in the strain energy. So a large decrease in strain energy going from 4-membered rings to 5-membered rings. When we get to the 6-membered ring, we see that the strain energy here is only 1 kilocalorie per mole. Now remember that that's a really small amount of energy. Okay, the HH Eclipse, which we saw recently, is worth 1 kilocalorie per mole, readily available at room temperature. So this is not a lot of energy. So because of that, we would say that cyclohexane itself is strain-free. Okay, so that's one of the important take-homes from this set of data. And again, not numbers you have to memorize. You might look at the trends going from cyclopropane to cyclohexane. Notice that the strain energy decreases, and we're going to look at why that is right now. Okay, so we're going to look at the first 3 rings. So cyclopropane, cyclobutane, and cyclopentane in this video. So the first thing is that way back in the day, everybody thought that any cycloalkane was flat. They thought they were all flat. That is mostly wrong. The only one that is flat is this one, cyclopropane. Okay, now that's because 3 atoms, when you have 3 atoms in a ring, they all have to be in the same plane. One can't be out of the plane of the other 2. Okay, so cyclopropane itself, the structure can be drawn something like this. So notice again, you've got these 2 bolded bonds that are coming out toward you. And then you have hydrogens, 2 hydrogens, a pair at each of the carbons. So the first thing to think about is the hybridization of each of these carbons. What's the hybridization of each of the carbon atoms in cyclopropane? Hopefully you said sp3, and if you did, you'd be right. So because these are sp3 carbons, the expected bond angle around them is going to be around 109.5. In cyclopropane, the actual bond angles so this would be the C-C-C bond angle, so right through here, is more like 60 degrees. And so that's a significant deviation from the ideal bond angle. So what that means is that you have angle strain. Now, if we think about some of the other sources of strain that are possible here, if we look at the structure of cyclopropane and think back to the structure we saw for eclipsed ethane, So here's eclipsed ethane. So if you were standing here in cyclopropane and looking this way, here's you, or if you were standing here and looking down the carbon-carbon bond in ethane, you'd be seeing very much the same thing. So here's the bond you're looking down, and what you're going to see is that you have 3 sets of eclipsing hydrogens. Okay, so it looks the same as cyclopropane. So cyclopropane and eclipsed ethane have a lot of similarity when we look down any of the carbon-carbon bonds in cyclopropane and compare that to looking down the carbon-carbon bond in eclipsed ethane. So what that means is that there's torsional strain, just like we saw in eclipsed ethane. So all these pairs of hydrogens are involved in eclipsing interactions. But remember, those hydrogens, because of the length of the carbon-carbon bond, are not close enough to each other to contribute any steric strain. So there is no steric strain. Let's talk a little bit about the bonding in cyclopropane, because the bonding is a little bit interesting. So for a typical bond between 2 sp3 hybridized carbons, remember that what you have is an sp3 orbital on one of the carbons with 1 electron in it. And that's going to overlap with an sp3 orbital on the other carbon that also has an electron in it. So the overlap looks something like this. Let me touch this up a little bit. So it looks something like this. But let's look at a picture of cyclopropane. So here are 3 carbon atoms. And here are the sp3 orbitals on each of the carbons. And just like we saw in previous examples, there's a pair of electrons associated with each of these bonds. Okay, now the bond axis, or the bond axes, I should say, between all of these pairs of carbons, I'm going to draw in as dashed lines. Now, really what we would prefer would be that those orbitals align along, or they overlap along the bond axis for the strongest bond. That's going to give you the greatest extent of overlap. Okay, just like it's shown in the picture directly above. But that's not the case. Because of the angle strain in this, the orbitals are sort of pushed out or bowed out, and so the shape of the electron density in the bond is more like this than it is like the picture up above. So it has that sort of curved shape. And because of the shape, people actually do call these banana bonds, because of the shape of the electron density cloud in that bond. So in the banana bonds in cyclopropane, the orbitals are not aligned along the bond axis, even though these are sigma bonds. They get bowed out or bent as the molecule tries to relieve the angle strain unsuccessfully. The result, as we can see in the pictures above, is diminished overlap. So the extent of the overlap between the two sp3 orbitals is diminished. You have less overlap, which leads to weaker bonding. Let's see what cyclobutane does to get around some of this. So here's cyclobutane. Now, cyclobutane has one more carbon than cyclopropane, and here's a picture of its structure. This is the major conformation of cyclobutane, and it's called a puckered conformation. So in the puckered conformation, as you can hopefully see in the picture, 3 of the carbon atoms are in the same plane. So I'm going to highlight 3 of the carbons in yellow, but a 4th is able to come out of the plane of the other 3, unlike the case that you have with cyclopropane. So one of the carbon atoms is not in the plane of the other 3. That's a lower energy situation than having all 4 carbons in the same plane. If all 4 carbons were in the same plane, then you'd have a larger amount of torsional strain. You'd have more eclipsing interactions. So the puckered conformation is lower in energy than having all 4 of the carbons in the same plane. And the reason for this is that the puckered conformation relieves some, but not all, of the torsional strain. Let's think about the bond angles here. The carbon-carbon-carbon bond angles in cyclobutane are 88 degrees in the puckered conformation versus 96 degrees when the molecule is in a transient planar conformation. We call that a planar, let's go backwards here, a transient planar state. Okay, what do I mean by that? Well, as it turns out, it's not always the same carbon atom that's out of the plane of the other 3. They all take turns, and they take turns by way of rotation around each of the carbon-carbon bonds in the molecule. So all conformational analysis, remember, is based on rotating around these single bonds. So rotation around those bonds, which is going to be a bit diminished because of the cyclic structure, is going to allow a temporary transient planar state as you go from one puckered conformation to another. Okay, so if this is the case, if the bond angles are 88 when the molecule is puckered, but they're 96 when it's in a transient planar state, then what's more important, apparently, for cyclobutane to do? Is it more important for it to relieve torsional strain, or is it more important for it to relieve angle strain? The data tell us it must be more important to this molecule to relieve its torsional strain, or to relieve part of the torsional strain. Because remember, it's the puckered conformation that relieves the torsional strain. However, the puckered conformation has more of a deviation from the ideal bond angle of 109.5 than does the transient planar state. So the molecule takes a hit, as it were. It accumulates a little more angle strain, but the trade-off is it gets to relieve some of the torsional strain. So by puckering, even though this introduces more angle strain. Okay, remember when you go from a 4-membered ring to a 5-membered ring, there's a big decrease in the strain energy. And so with that additional carbon atom in cyclopentane, you have much more conformational flexibility. So cyclopentane can adopt this conformation. This is its major conformation. It's called the envelope, and it kind of looks like an envelope. So this is the major conformation. And this relieves the majority of cyclopentane's torsional strain. The torsional strain that it would have, that is, if it were planar. So this relieves the majority of its torsional strain. Now let's think about the angle strain. The carbon-carbon-carbon bond angles here are 108 degrees. Well, that's pretty close to 109.5. So there is no angle strain in cyclopentane. So our next task is to look at cyclohexane, and that's going to take us some time. So we will wrap this video up and pick up cyclohexane in the next one.